Hi, my name is Peter Bross. I'm a developer advocate at Autodesk, and in this talk, I'm joined by Greg Fina from AWS to talk about advanced design chatbots with Autodesk Platform Services and Amazon Bedrock. This is a continuation of a talk we did with Greg last year, where we try and inspire developers to build their own chatbots by sharing results of our experiments. Now, what is a chatbot? If we simply follow the Oxford Language Dictionary, it is an AI system designed to simulate natural language interaction with human users. And designing chatbots specifically is a system that would be able to answer your questions about your own design data using simple natural language prompts. Now, what would such a system need? The chatbot would, first of all, need to be able to access your design data. It would need to be able to understand the structure of the data and to actually communicate with the APIs that enable this access. It would need to generate and execute queries over the data, potentially including filtering, aggregations, or pagination. And finally, the chatbot would also need to understand the data retrieved from the APIs in order to be able to provide natural language answers. So once again, I'm Peter Bross from Autodesk. I'm a developer advocate for Autodesk Platform Services, and as part of my job, I am exploring ways to integrate our platform with other systems, in this case, large language models. And now, Greg, over to you. You want to introduce yourself?
Thank you, Peter. My name is Gregory Fina. I'm a principal solution architect with AWS focused on generative AI startups. I'm here to work with Peter on what we did with Amazon Bedrock in bringing generative AI into the APS data models. With that, we're going to spend the time talking about various categories today. First, I think what we want to do is talk about how the different ways we access data within Autodesk Platform Services. Second, we're going to talk about a bunch of techniques that are used in generative AI to help you get back the answers that you want. Third, we're going to talk about tools and frameworks, and we're going to spend a lot of time sort of demoing Amazon Bedrock integrated into the APS viewer. And those will be our examples, where we're going to do examples on model derivative service, model properties, and also the AEC data model, which uses GraphQL. And we'll save time at the end for questions and answers. As with all Autodesk presentations, there's always a disclaimer. I'm sure by now most of you have read this about 20 times, but just in case you're curious about the summary of this, basically Autodesk is telling you not to buy anything, but I'm hoping by the time we finish this that you've put your credit card into the console and you've started to buy Amazon Bedrock. And one last disclaimer. To be honest with you, by the time we finish this presentation, whatever you learned in it, as fast as generative AI is moving, is going to be out of date. So please keep that in mind.
Thank you, Greg. All right, so let's start by looking at the different ways that Autodesk Platform Services provide that let you access your design data that you could potentially use in your custom large language model setups. Our platform provides several APIs that are meant to give you access to metadata in your designs hosted in different Autodesk products. Model derivative API is a good example. This is a very basic service responsible for extracting information out of your design files. This is something that we actually based our first talk on, but there's more options. There's also the model properties API, which is available for models hosted in Autodesk Construction Cloud. And then, as Greg already mentioned, we also provide AEC and manufacturing data model APIs. In this case, this is a GraphQL API that you can also use to extract all sorts of information out of your design data. These are the three services we will be focused on in this talk. There are other options. You could potentially also use data exchange or design automation API, for example, to extract information out of Revit designs using your custom Revit plugin. And even after loading designs into the client-side JavaScript component that is our viewer, you could use viewer SDKs to extract information out of your designs, but these are considered out of scope for our talk today. All right, model derivative service, again, very basic API, something that has been part of our platform pretty much since the beginning when it was still called the View and Data API. The model derivative service is responsible for extracting all sorts of what we call derivatives out of your design files. These derivatives could be thumbnails, 2D drawings, 3D views with textures, any kind of logical hierarchies, or individual element metadata. This information can then be this extracted data can then be accessed through a REST API, and we provide an endpoint that lets you query your data using basic filtering. So for example, you can specify that you're only interested in properties for certain object IDs. The API also provides basic projection. So you can say, for the results, I'm only interested in, let's say, dimension data and nothing else. The endpoint then provides pagination so that if the model is really large and complex, you don't need to overwhelm our servers and your client. You can really start streaming the results back to client in pages. And unfortunately, there is no aggregation support at this time. So for example, if you wanted to do something like calculate the total volume of data of, let's say, elements in your design, this is something you would need to do in post-processing on the client side. And also, there is no property schema because for different file formats, for different design file formats, the properties that you retrieve using this API may be completely different, and you will never know beforehand what properties are actually available on individual elements. The next one, the ACC Model Properties API, as I mentioned, this API is available for models specifically hosted in Autodesk Construction Cloud. It's also a REST API. It's a little bit more powerful than the standard model derivative in that, first of all, it lets you build indices of properties of your specific design. In this index, you can then find a list of all properties available in your design, and then you can start querying these for actual values for specific elements. The Model Properties API also lets you calculate diffs between different versions of your design. The service uses a custom query syntax that you can see in this picture on the left, where you can, again, specify a filter query. So for example, you can specify that you're only interested in results for elements where a certain property is set to a specific value. And then aggregation is also supported so that as part of the query, you can also specify that on the output, you're interested only in certain properties. And maybe you want to calculate a sum of values in a specific column or in a specific property. And again, compared to the model derivative service, in this case, you can actually get the list of the schema, basically, of your design, getting an exact list of properties that are available in this design, and you can get information about their type, units, and additional information as well. And the third option that we will be exploring and showing actually our examples for today is the AEC data model. As Greg mentioned, this is a GraphQL API. So this is something that a GraphQL interface lends itself very nicely to how we actually represent data of your designs in our data models, because the data is actually represented as a graph of nodes connected by edges. So in this case, a node could be a category or an instance or a geometry, and then edges would then represent relationships between these elements, between these entities in your design. The Data Model API provides basic filtering capability. So you can say, for example, I only want to list elements where the category is walls. And also for then filtering within the properties of the elements, you can filter these using an RSQL syntax. This is a third-party syntax that we've adopted so that you can also provide more complex queries, so that you could say, for example, return all elements where length is more than 10, less than 20, or where the area is more than 20 square meters. Aggregations, again, are not supported in this case. So if you wanted to calculate things like sum of volume or total volume, this is once again something you would need to do in post-processing on the client side after fetching all the required information from Data Model API. And also in this case, the property schema, in other words, really a description of what properties are available on your design elements, in this case, can be retrieved using the GraphQL API as well. So just a summary, a simple table here, really outlining the three options: the model derivative API, model properties, and data model API, and showing basically when it comes to querying or filtering, what's available. So for queries, again, for all three options, all three options provide certain querying language that let you specify what types of objects you're interested in. All three are custom. So this is something that potentially, as you will see later, you will need to sort of teach to your large language model. Filtering also supported. Projection. So again, being able to specify what parts of the results you are actually interested in. And aggregation. So in this case, aggregation is only available in the ACC Model Properties API. And the schema, description of what properties you actually have available, is available for model properties and the data model APIs. All right, now in the next section, let's take a look at some of the techniques, some of the current standards that are being followed when implementing large language model-based solutions. One thing that, since this is an advanced talk, we want to really follow up on the basic ideas we covered in the first talk. Here, we're starting to talk about agents and tools. So what does that mean? Instead of having a simple while loop of like question, answer, we want to introduce or talk about the concept of agents. And really the definition of what's an agent, it's really an AI system that can plan out a set of steps for itself to take. It can call into tools provided by the developer to retrieve whatever information or achieve whatever results it's trying to get to. And it can also, in retrospect, look at its own results and review them. And if needed, actually go back to the beginning and again, start planning out the set of operations for itself. And a tool, in this case, is really, you can think of tool as any arbitrary function that you as a developer of your chatbot can provide to the agentic system. And for each tool, you will provide some sort of description and let's say a schema describing the type of data that this tool requires on the input. And then by providing this collection of tools, as you can see in the diagram in the middle, the agent, the large language model, can actually look at all these tools that are available, and it can try and automatically decide which of these tools it should probably call and get results from to actually be able to proceed with the task that you provided to the system. So again, the diagram here sort of at the high level highlights this general idea where when the agent gets a task from a user, it plans a set of steps for itself to follow. And for each step, it is considering calling into a specific tool that might have been provided to it. And it's processing then the results from the tool call. And in the end, it's reviewing the results that it arrived to. And if needed, it actually circles back to the beginning and starts to rethink or maybe adjust the direction a little bit more. And these are agents and tools. And these are now supported in many different models and frameworks, Anthropic, Llama, Cohere, Amazon Bedrock, and as you will see later, supports agents as well. Okay, Greg, over to you.
Yeah, I think what we want to do is take a step back though and break down an agent, right? Like, because an app is going to make calls into agents. So if you think about our simple diagram on the right, you have an app, right? And then you're going to move forward and it will enhance and talk to the agent, which will then make function callings to various functions, which in the previous diagram we call tools, to make it a very interesting implementation. Now, if Peter walks through this, you'll see a little bit of automation on this slide as it sort of shows you that the agent's there, and then the functions are step 2, and there's many implementations of this. And you, as the previous diagram showed, you can get very complex and sort of changing your agents together. But what I want to do now is sort of take you through a simple workflow. So this workflow, right, if you think about it, they build on existing enterprise resources. So I don't know about you, but one of my favorite things is vacation time. So let's think about when you file a vacation request, all the things that need to happen. And if you think about it, what you're going to do is you're going to sit down at your laptop, and then you're going to move forward, and Peter will advance the slide, and you're going to hit the time off agent, which is going to go into your sort of HR policy and knowledge base and get you the policy. Then with the next thing, you're going to get your sort of time off bounds, which might have to hit both a vacation microservice and a vacation database. And then your last thing is you're going to put in a request for leave of absence. So in this, what we've done is we've now taken, a very trivial task that most people do in scheduling time off, and we've used existing agents to go make that happen. So let's be clear, as part of this, now that we've gone through agents, right, there's many techniques to get to the answers. And one of the most common one is prompt engineering. So prompts are what you actually pass the agent or Bedrock or any large language model. And so what you want to do when you do that is you want to basically make sure you're specific and clear. And the other thing is if you use LangChain, which we'll talk about later, you can refine your prompts in the next one to get better answers. Next, you want to make sure you provide it as much context as possible. Peter, I think you went too far. You want to provide context, and then you want to use examples and constraints to help guide the tone and the language. For instance, one of the things you're starting to see now in schools is the use of these large language models. Well, an answer for a 5-year-old is going to be quite different from somebody that's in high school. And so you'll actually be able to use constraints about tone and language and age and so forth. And then the other item is, remember, this is an iterative process. You prompt a large language model, you get back an answer. You can ask the large language model to refine the previous answer it gave you. And then the other technique is RAG. RAG is really stands for augmented generation. And the idea behind this is I can basically put a bunch of data into a knowledge base in chunks. Typically, it's stored in a vector store, so it's searchable. Think about like OpenSearch. And I embed the data. And what RAG is going to do is it's really going to implement a k-nearest neighbor search and to pull relative chunks of information back to help you answer the question. And so when you're dealing with sort of large language models such as Anthropic or Cohere or Meta, one of the things you may want to do, instead of trying to retrain it, or some people will call fine tuning, is you would actually use RAG to help you get answers specifically back. So in the case of the knowledge base in the previous example around time off, you could actually take some of that information and you could put it in RAG, you could chunk it out and store your policies as vectors and allow the system to use that to go get the correct answer. So if you think about this, you're going to have a data ingestion workflow, right? Because you're going to basically have to get your data into a vector store. And so you're going to have enabling models, and enabling models are interesting because them themselves are sort of large language models. And then you're going to have your data source. And that's going to feed into your vector store. And if we advance the slide, you'll see that you're going to use an embedding model, which in itself is going to be a large language model, which is going to allow the user, when we advance the slide one more time, to basically put in prompt, and it's going to use the context in the vector store to augment the prompt and go to the large language model so we get a more specific response to our specific question, potentially about our specific data or our specific use case. And so I did mention fine-tuning a little bit earlier, and I think fine-tuning is very complicated, and it's not for everyone, because you're going to basically start with one of these existing large language models, or maybe multimodal models if you're dealing with geometry data, and you're going to sort of retrain it on your own data. It's highly expensive. It's because it requires you to have GPUs, and depending on how much data and how much retraining you're going to do, it could require a lot of time. However, if you want your model to be specific, so for instance, you might use the HR example, maybe you only want a model that understands all of HR properties and only has HR properties in it. And so the question becomes, do you fine tune, say, something like Llama or Claude from Anthropic, or do you build your own model? And sometimes, in some cases, it's actually better to fine tune when you have specific use cases, giving it the additional data sets to move it forward.
Thank you, Greg. All right, so in this next section, let's take a look at some of the tools or frameworks you have available when you're ready to start building your own design chatbot, because you don't need to start from scratch and reinvent the wheel. A very popular framework in this space is called LangChain, or its peer project, LangGraph. LangChain is a framework for building LLM-powered applications. It can connect to Anthropic, Llama, Mistral, Bedrock, as you will see later, and many others. It's a collection of components that you can combine in your sort of flows. These components include chat models, embedding models, document loaders, parsers or chunkers, vector stores, retrievers, or, as we mentioned earlier, this concept from agentic flows. It lets you define tools as well. There are building components as well as third party, and the ecosystem is really large. And the framework itself, LangChain, is available for Python and JavaScript. This is what we, again, used as part of our first talk. This is what the framework you would probably use for this question, answer, endless loop. LangGraph, on the other hand, is more of an orchestration framework for agents. So this is where you can actually build more complex sort of graphs, where you can connect agents to tools, and you can give them intermediate steps to plan their sequence of actions, or actually for them to be able to sort of review the results that they've arrived to and see if maybe they want to go back and change their plan a little bit. And LangGraph also supports streaming, so that you can actually you can follow this basically thought process of your design chatbot before it actually arrives to a result. And as well as human in the loop support in situations where at some point the chatbot may actually may depend on some input from the user. There are other tools and frameworks as well. Another popular one is called Llama Index. This one is very popular for its document parsing capabilities. So imagine if you wanted to, for example, build your own knowledge base. For that, you would probably need to pull information from different sources and process it so that you can actually build your knowledge base based on some reasonably good quality data. So Llama Index is very popular in that space. There's also the TypeScript AI framework for building agents called Mastra, and there's Haystack, Crew AI, Docling, another good solution for parsing documents for ingestion into LLMs or knowledge bases. There's really too many of them. And talking about knowledge bases, there's also third-party options, like these vector stores that Greg mentioned, such as Pinecone, Chroma, or Weaviate. You can think of these as basically databases that can store data in a multi-dimensional space, meaning a space that may have 1,000 dimensions. And these dimensions you basically define using the embedding models that were also explained earlier. All right, Greg, back to you.
Yeah, thanks, Peter. So I think that we've covered some generic goals. Well, AWS has its own generative AI stack. If you want to go train models, we offer you GPUs. We have NVIDIA GPUs. We also offer Amazon built Trainium and inferential GPUs. We have Amazon SageMaker if you want a little bit of managed infrastructure, but you still want to have control your own model, control your own data. Next, we offer Amazon Bedrock, and we allow you to sort of bring your data, keep your data secure, not provide it to the model providers, but be able to call their models in a very secure way. And lastly, at the top of the stack, for instance, if you want to go build code, you can use Amazon Code Developer. Actually, for the original DevCon presentation that kicked this off, I used Amazon Q Developer to see how it would work in building out our original talk. And there's also Amazon Q for Business, which allows you insights and automation, and it's more in sort of the agent space. So this allows you to build whatever you need with the most cost-effective infrastructure, keeping your data secure and private, as well as allowing you to build the next wave of AI applications. And so since so much talk on this is based on Amazon Bedrock, because we basically use Amazon Bedrock in APS, I think it's good to understand what Amazon Bedrock is. And Amazon Bedrock specifically provides you an API for leading foundational models, whether it's AI 21 Labs, Anthropic's in Claude, Cohere's, Meta's Llama, Stable AI, our own Amazon models, which now include Titan and Nova. We give you access to choice about model. Secondly, you're able to fine tune in Amazon Bedrock. So you can have model customization. It has some built-in RAG capabilities, as well as now introduces the step of agents where you can execute multiple multi-step tasks. And again, lastly, it's very secure. Privacy, your data is protected. None of the model providers are seeing your data. And lastly, it allows you to build some data governance around your data. And so here, just to show you the choice of choices, there are a lot of models that you can use on Bedrock. And our philosophy is to allow you access to all the great models. And there's even a marketplace now in Bedrock so that you can actually leverage other people's models with Bedrock. And so now we're going to kind of get into the examples. So I think what we're going to do is we're going to start out with a very basic one around the model derivative service, and we're going to step our way up to GraphQL. So similar to the demo from our previous AI talk, we're going to use basically selected design data. We're going to put it in a SQLite database. We're going to build a LangChain agent to basically go query the SQL data. And we're going to all do this via natural language prompts. The code on this is very small. And so with that, I think now we'd like to sort of show you the demo. So as you can see, we're running a local Python server. We're going to go to the web browser to do the handshake authentication for that web server. And now we're opening up our files. I think we pretty much open up the common Shodan Tower one. I think most people who have seen any presentation on Autodesk has seen this example, this multi-use facility. We're going to ask it a basic question. You'll see it processing the basic question over in the chat window, and it gives the answer. And it shows you sort of how it chains the information together to get the answer. So, and the answer's back very quickly. Now, if we go back to the console, there's the answer that we just had. And obviously, we're taking advantage of APS capabilities by just simply clicking on the JSON property IDs to bring up the item. We're going through, and now we're going to show you the model properties of that object. And we're back to the full building, and we're going to ask it. I think this one, if I remember correctly, asks it about the volume. And again, you can see that it's running and we're outputting what's happening behind the scenes. And you can see that it's generating SQL queries to go get this data from the SQLite database. So it answered the question. I believe
And that is it.
that
Yes.
is the end of the demo.
First demo. Thank you. Thank you, Greg. All right. The next example is one based on the ACC model properties. In this case, we are advancing the complexity of the solution. We're introducing multiple custom tools. So while in the previous example, we used just a built-in tool available in LangGraph to basically generate SQL queries from text prompts. In this case, we will provide a couple of custom tools to our agent. One, we will include a tool for building the index of all properties for a specific design so that the large language model actually knows what kinds of properties are available in that design when it wants to query it. We provide a tool for retrieving these properties. We provide a tool for actually executing a custom query over that data. And we also include a small tool for processing because the data that the agent will receive back from our APIs will be all JSON. We also include a tool that can process the JSON data using the third-party utility called JQ that can be used to extract and process JSON data in different ways. Now, also, what's important, since I mentioned earlier, the AEC Model Properties API uses a custom syntax for querying, for building queries over the data. We will need to teach the large language model what this syntax looks like so that the agent can actually generate these queries properly. We do that using what's called system prompt, where we basically provide a static description and we provide a set of instructions that we feed into the beginning of the context window. So every conversation that you will start with this assistant will, under the hood, always start by feeding the agent a set of basic instructions explaining that this is, a model properties API that has these and these characteristics, and that we also include a markdown basically explaining the model properties query language syntax together with some examples, again, to improve the chance of the agent actually generating proper queries. So let's take a quick look at our demo. So just like before, we are starting our Python server on localhost. And we visit the web page of our server. Just like before, we navigate through ACC projects and folder structure to get to a specific file. Once again, here we will use the Snowden Tower architecture model, and we can start asking questions. For example, what are the walls with the largest area, for example? And again, we can look at the log file to sort of follow the thought process of our design chatbot. So first, you'll see it will try and basically start building the index of properties. It actually laid out this 3-step plan for itself. It will try and build the index of properties and then retrieve these properties. That's where we're at right now. So now the agent knows what kind of properties are available. And now it will try and basically start collecting the areas of the individual elements so that it can find the 5 largest ones. Here, what we do is actually, we intentionally throw an exception from our tool when there's too many results because we don't want to exceed the size of the context window. So we are basically being mean to our agent and we're forcing it to reconsider the queries that it's generating so that it gets fewer results. Here now it's been able to, basically it's now trying to, first of all, get the largest available area, and then based on that, it can then adjust the generated query to get the information it needs. All right, so here it found 3 elements with the largest area, but of course we asked for 5. So now it's actually trying to execute additional queries into the Model Properties API. And now it identified several objects with area of, let's say, 5,000 square feet or 3,000 square feet. And again, we can double check that it's not hallucinating any information, that the area is, in fact, in this case, 1,768 square feet. And just like before, we can try and test an aggregation query. So we're asking for the total volume of all elements. And here, since, as we mentioned earlier, model properties have the benefit of actually providing aggregation functions so that you can ask for a sum of volumes or areas and actually issue this query into our servers, into Autodesk Construction Cloud, and the sum will be calculated on the server side. In that case, it makes it very easy for the model to actually get that total volume. So as you can see here, we already have the total volume, but the agent is actually trying to find some of the largest elements to sort of like not only give you just the answer of the total volume, but also the elements that are contributing to the total the most. So here you can see it's 103,000 cubic feet. And these are some of the elements that are really contributing to the total. All right. That was our second example. And the final one is the assistant based on our AEC data model. So again, we're stepping up a little bit in terms of complexity. We are, again, introducing a couple of custom tools. We provide the agent with a tool that can execute a GraphQL query against our data model API. We once again provide the agent with a tool for processing JSON data using JQ. And in this case, we're actually introducing RAG, the concept that Greg explained earlier, the retrieval-augmented generation, where we basically, instead of us putting the complete list of properties into the context window when chatting with our chatbot, this list could be potentially really, really large, and the context windows of LLMs are still somewhat limited nowadays. What we want to do instead is we want to actually build a vector database of all the different properties that are available in our design. And we later want to use the retrieval-augmented generation to only cherry pick property definitions that are most relevant to whatever the question the user provided. And then only based on this limited subset of the full property definition, the agent can then proceed and build GraphQL queries. And similarly, with the second example here, we also provide a system prompt, basically a bunch of Markdown files where we provide basic instructions. We explain how filtering and pagination works in the AEC data model GraphQL API. We provide some examples. And we also include the description of the entire AEC data model GraphQL schema. So every single object and method and parameters that are basically defined in the AEC DM GraphQL API that the model needs to know in order to be able to create valid GraphQL queries. All right, now let's take a look. Just like before, again, this is a Python server application, and we are running it on localhost. And we provide a similar looking front-end experience. In this case, however, we're not searching through files because in AEC data model, we don't work with files. We work with the concept of element groups. But here you can see we have a bunch of element groups. We will pick the Snowden Tower architecture again. And we will try our first prompt, which will be, what are the top 3 walls with the largest volume? And now, again, let's go look at our log file to follow the thought process of our design chatbot. You will see that it will start, again, planning out the set of actions, the 3 steps for itself, and it will start calling, executing GraphQL queries. The first time you see it doesn't get any results, so it's trying to rethink and go back and try and basically use slightly different filtering in the auto-generated GraphQL query. Now it is getting results. However, I'm not entirely sure that this is the right thing. I'm asking the client, hey, I don't think you've gone through all the walls because there is this concept of pagination, and I haven't seen the model in its thought process to actually go through additional pages. And as you probably know, okay, now it's being very apologetic and trying to fix its mistake. But now it's actually following the pagination capability of our API. It's calling additional queries with additional what are called cursors. So in our GraphQL API, a query can return a bunch of results with a cursor that points to another page. So now the large language model is actually calling these until it gets through all the pages. And with this, the model should have enough information to answer our question. As you can see here, I'm not entirely sure. So we received, okay, this actually might be right. So we check the properties of this basic wall. We see that it's the volume is 41 cubic meters, which corresponds to the data that the assistant provided. So, you know, that it's not hallucinating. Although, again, we want to be really sure that the agent actually follows, that it goes through all the pages. Otherwise, of course, the results that it provides will not be correct. All right, and Greg, back to you.
So in case you fell asleep, we decided to ask Bedrock to summarize our entire presentation. And this is the summary out of Bedrock. I'm not going to read it all, but for those of you who are sleeping through our presentation, now's the time to wake up, take a screenshot with your phone, and review it later, and hopefully you'll have some knowledge on what we presented here. And does anyone have any prompts? Well, I guess we should ask questions, not prompts.
Awesome. Thank you so much, Greg.
Thank you, Peter. It was a pleasure working with you on this.
Pleasure as always.